Could Proxima b be another Earth-like planet? This question remains open, but it's a speculation that stirs immense curiosity. The idea of finding an alternative habitable planet, or perhaps even alien life, has long fascinated humans, pushing us to constantly probe the cosmos. While scientists have found numerous exoplanets, Proxima b has drawn special attention due to its characteristics and proximity to our solar system. Signals coming from Proxima b have spurred even more speculation, leading many to wonder if there might be something unique about this exoplanet. However, despite these intriguing signs, we have yet to determine whether these signals truly originate from the planet or if they're merely echoes of our own scientific communications. Often, these signals turn out to be echoes, but scientists continue their efforts to discern their origin. If these signals do turn out to be from Proxima b, they could provide significant insight into whether alien life exists. The recent detection of artificial lights on Proxima b by the James Webb telescope has only added to the intrigue, as such signals could potentially be indicators of life or advanced technology. If you're curious about our progress in discovering life beyond Earth, consider subscribing to our channel, where we delve into the mysteries of outer space and discuss the latest scientific innovations. If you find this content exciting, please comment below and share this video with friends who share your interest in space exploration. Now, let's explore more about Proxima Centauri and why Proxima b has captivated scientists around the world. Proxima Centauri, located about 4.2 light-years away, is the closest star to our solar system. Classified as a faint dwarf star with a spectral type of G0v, Proxima Centauri is an integral part of the Alpha Centauri star system. Historically, it was named Alpha Centauri and Horologium by the astronomer Johann Bayer in 1603, who named it based on its positioning in the sky relative to other celestial bodies. This name highlighted the star's ascension at noon, when the sun and moon were aligned with it in a rare astronomical event. Also known as Alpha Centauri A or Alpha Centauri, Proxima Centauri is not alone in its stellar system. It has 3 other main stars aligned with it, with Proxima itself positioned at the system's center. Besides these primary stars, there are 2 faint dwarf stars, Alpha Centauri A and Alpha Centauri B, sometimes referred to as Rajucataris. Although these 2 dwarfs make up the majority of the system's mass, their faintness makes them invisible to the naked eye. Located just 0.3 inches from the border of the Plough asterism within the Centaurus constellation, Proxima Centauri holds a unique place in our galaxy's structure. What intrigues scientists most about Proxima b is its rocky surface and potential to support life. Proxima b, unlike many gas giants or icy exoplanets, is rocky, increasing the possibility it might be able to host life. While many aspects remain speculative, scientists consider Proxima b a viable candidate for habitability due to its Earth-like size and the distance from its dwarf star, Proxima Centauri. The location of Proxima b places it within the so-called habitable zone, a region where conditions might be suitable for liquid water to exist on the planet's surface. Although the search for extraterrestrial life remains in its early stages, the similarities between Proxima b and Earth have encouraged scientists to explore it further. However, Proxima b is not without its challenges. While its proximity to Earth makes it an attractive subject for study, certain aspects of its environment present difficulties for life as we know it. One primary concern is the intense radiation from its host star, which emits far more ultraviolet radiation than our Sun. Proxima b is located significantly closer to its star than Earth is to the Sun, leading to constant bombardment by extreme ultraviolet radiation. This radiation level is hundreds of times higher than what Earth receives from the Sun, and is so strong that it could strip away light elements like hydrogen from the planet's atmosphere. Over time, this intense radiation could erode heavier molecules such as oxygen and nitrogen, elements essential to most known life forms. While some may argue that Proxima b's position in the habitable zone makes it suitable for life, distance alone is insufficient. Habitability also depends on the presence of liquid water and a stable, life-supporting atmosphere. Currently, there's no direct evidence of an atmosphere on Proxima b, and scientists continue to study whether it has the protective layer needed to support life. Earth's atmosphere, for instance, is a key factor in regulating our climate, supporting surface water, and protecting organisms from hazardous space weather. This combination of factors makes Earth unique in its ability to sustain life, unlike Mars, which lacks the necessary atmosphere despite its position near the Sun. If you're still with us and haven't subscribed yet, take a moment to hit the subscribe button to support our work. we're committed to bringing you more content on space exploration, the search for extraterrestrial life, and other scientific advancements. Now, let's delve into why scientists believe the James Webb Telescope could help reveal whether life exists on Proxima b. The James Webb Telescope, which launched in 2018 after numerous delays and modifications, is a technological marvel built specifically to observe distant objects in infrared light. One of its missions is to help scientists investigate planets like Proxima b by capturing infrared signals that may reveal atmospheric properties or surface conditions. Dr. Avi Loeb, an astrophysicist, explained that a planet like Proxima b, if it absorbs light from its star, may re-emit it as infrared light. The James Webb Telescope is specifically designed to capture this type of infrared radiation and analyze it for patterns that could indicate water, an atmosphere, or even artificial light signatures. Space telescopes like the James Webb are particularly advantageous compared to ground-based observatories, as they orbit above the Earth's atmosphere. This positioning allows them to avoid atmospheric distortion and view objects in deep space with unprecedented clarity. Ground-based telescopes often struggle with atmospheric interference, which limits their ability to observe faint signals or fine details beyond our solar system. By observing from space, the James Webb Telescope offers a clearer, uninterrupted view of planets like Proxima b, potentially bringing us closer to understanding whether they could host life. The potential of Proxima b remains a topic of speculation, but with the James Webb Telescope and advancements in technology, we may one day know if this exoplanet is more than just a rocky sphere. Space telescopes provide unparalleled advantages, particularly in their ability to observe the universe without interference from Earth's weather patterns. Unlike ground-based telescopes, which are affected by cloud cover, atmospheric distortion, and weather, space telescopes give astronomers a consistent, clear view of distant celestial objects. This clear reading is crucial for studying planets, stars, and galaxies in detail. However, the main downside to space telescopes is the high cost of maintenance and repairs. Unlike ground-based instruments, repairing a space telescope often requires an expensive mission into space, especially if a critical flaw is detected post-launch. A single minor flaw can necessitate a full mission to correct it, which can be financially and logistically challenging. This limitation is particularly relevant for the James Webb Space Telescope JWST, which is positioned over 1.5 million kilometers from Earth, far beyond the reach of any human rescue or repair mission. Despite this distance, the James Webb Telescope represents an enormous leap in observational power. With its larger mirror, it can peer back in time to nearly the beginning of the universe, approximately 13.7 billion years ago. This ability is made possible by the fact that the further away an object is, the further back in time we see it due to the time it takes light to travel across space to reach us. The telescope's ability to observe in infrared light, a longer wavelength than visible light, allows it to detect more distant galaxies that are otherwise obscured to us. Observing objects like planets in the infrared spectrum is advantageous because it reveals details that would otherwise be hidden in visible light. With the James Webb, studying planets like Proxima b has become more feasible, and astronomers now have more confidence in detecting potential signs of life or artificial illumination on distant planets. In exploring the concept of artificial illumination on Proxima b, scientists Avi Loeb and Jacob Tabor developed a theoretical scale for detecting artificial light on a planet's night side. This scale represents illumination as a fraction of the brightness of the day side. At 0%, the night side is entirely dark, with no artificial lighting, while at 100%, the night side would be as bright as the day side due to artificial sources. If there were a hypothetical civilization on Proxima b, artificial light similar to early Earth's illumination would be detectable. Studies suggest that if Proxima b's night side reached an illumination level equal to 5% of its natural day side brightness, the James Webb Telescope could detect this artificial light with about 85% confidence. If illumination reached 9%, this confidence rises to around 95%. Although 5% illumination might sound minimal, it's significant, given that Proxima Centauri, Proxima b's host star, is much dimmer than our Sun. The light reaching Proxima b is around 20,000 times dimmer than what Earth receives, meaning any artificial lighting detectable from such a distance would require substantial brightness. Even with this technology, detecting a civilization on Proxima b would be challenging due to the dimness of Proxima Centauri. Proxima b's orbit, which is very close to its star, likely results in tidal locking, where one side of the planet is perpetually daylit while the other remains in darkness. A civilization on such a planet might require bright orbital mirrors or other infrastructure to illuminate the night side effectively, enhancing visibility from afar. Tabor and Loeb's speculations add intriguing possibilities to our search for extraterrestrial life, though these remain theoretical without direct observational evidence.